Welcome to Unit 13, Part 1. In this unit, we are going to be continuing our study of momentum, focusing specifically on conservation of momentum. And to begin that discussion, what we're going to do is take a trip back through Newton's laws. So remember Newton's third law. Newton's third law is the one that said if object A exerts a force on object B, then object B exerts a force that's equal in magnitude but opposite in direction from object A. So we can write that this way. These two forces are equal in magnitude, but there's a minus sign to indicate opposite in direction. And now I'm going to take and make an assumption. And I'm going to make an assumption that whatever is going on with these two objects, these are the only forces that matter. So that I can say that this is the net force on object B. And this is the net force on object A. And I'm going to plug that in. So the mass of A times the acceleration of A now has to equal negative mass of B times the acceleration of B. So now I've combined Newton's third law with Newton's second law. And I'm going to make the same change of writing the acceleration as the change in velocity over time that we made when we developed the idea of impulse in the last unit. Okay, now let's think about these times. Notice the times do not have a subscript, and that is because they are equal. Why is delta t equal? Well, that's the time over which these forces act. And because they're a third law force pair and they occur simultaneously, if one stops, the other one has to stop. And therefore, the delta t's are the same. And because they're the same, I can cancel them. And on the next line, I'm going to take and write out the definition of change in velocity as final minus initial for both the mass A and mass B. Okay. And now just playing a little bit with distribution of the mass into the equation. Final B. And now I'm going to move everything that involves the initial velocity to one side, everything that involves the final velocity to the other side. So we're going to get MA VA final plus MB V. Guess I'm just kind of writing my subscripts in any order at this point. VB final equals MA VA initial plus MB VB initial. And so in this case, the final momentum of the two objects that are interacting has to equal the initial momentum of the two objects that are interacting. And we have just, starting with Newton's laws, derived conservation of momentum. So what conservation of momentum says is that in an isolated system, the total momentum of the system of objects is conserved. So notice, system of objects, conservation of momentum by necessity has to involve multiple objects unless you're dealing with like one object out in space interacting with nothing. The joy of conservation of momentum is that it is set up to deal with interactions. multiple objects bouncing off of each other or things splitting in two. So let's do a little bit of work to understand what this statement means, because we introduced a new concept here, and that new concept is system. So what is a system? Oh, we're going to start with isolated. Isolated means no net external forces. Okay, so remember way back here when I said the only force that matters on this object is the force that comes from the interaction of A and B. Therefore, I isolated my system when I said that. No net external forces. Okay, does that mean that there can't be other forces acting on the object? Not at all. There can be. But they have to somehow cancel, or they have to be somehow inconsequential over the duration of the interaction. One that often pops up that really throws students for a loop is friction. Yes, friction is acting during the interactions. Most likely, yes. But the effect of friction over the small delta t over which these interactions usually take place is so small that we can ignore it. Okay, so isolated means no net external forces. System is the collection of objects that you were looking at. In our derivation, the objects were A and B, whatever they happened to be. In reality, oftentimes in order to isolate a system, what you need to include also is the Earth, because of, again, friction. But often we can ignore that. I know it's this nasty, gray, hazy, yes, it's there, but we don't need it most of the time type answer. And I know that doesn't sit well, but it's the way it works. Okay, so conserved. So let's think about this. If I push on an object, it slows down to a stop. Where does the momentum go? So drawing the picture of what I mean. So here I have an object, looks like a block again. I give it a push, that gives it some velocity. So this would be the initial situation. And the final situation is it's moved a little bit down, and it is no longer moving. So momentum was not conserved here. Why was momentum not conserved? Okay, well, in this case, we have not isolated our block if we consider just the block as the system. Okay, and this interaction time is most likely fairly long. And over that interaction time, friction is going to matter. So this is a situation where friction does matter. Where does the momentum of the block go? Well, it goes into the earth and the surface. It could be things like the fact that the friction has caused the molecules in the surface and in the block to gain some thermal energy, and therefore they're moving faster. Any number of places. Okay. The point here is, in this case, our system was not isolated because we were only considering one block. We needed to consider the block and everything touching the block in this case in order to isolate it, because our interaction time was fairly long. So now let's go to one where we can have a long interaction time, but we don't need to worry so much about whether or not we're isolated. So now the question is, how does a rocket maneuver in space? And the answer to that question is the same as the one below it. How does a balloon fly across a room? So I'm going to endeavor to draw a rocket, because I think I can draw that better than I can draw a balloon. But, you know. Okay, so how does a rocket maneuver in space? So here's our rocket. It is moving, say, this way, but it doesn't want to move that way. It needs to make a course correction. So what does it do? Well, one of two things. It might need to speed up or slow down, in which case it fires the main thruster, or it might need to change direction, in which case it has these little thrusters on the side, right? But either way, when it does that, I'm going to deal with the main one because it's, again, easier to draw. We have gas that moves this way. So the gas gains some velocity that it didn't have when it was part of the rocket. And because we have gas going backwards, that means that the momentum of the rocket going forward had to increase. Okay, I will endeavor to draw the balloon and do the same thing. So here we have our balloon. Oh, that's not very good, but we'll deal with it. Okay, right now the balloon and the gas is all one piece, but when you release it, the gas goes this way, which means the balloon has to go that way. Again, conservation of momentum. Now we have two different ways of looking at motion that seem very related. Remember, we have kinetic energy, and that equaled 1/2 mv squared, and we now have momentum, P equals mv. Okay, there are some big differences between these, the biggest of which is that kinetic energy is a scalar and momentum is a vector. Okay. Other differences, well, both of them depend on mass, are proportional to mass, but kinetic energy is proportional to velocity squared, whereas momentum's only proportional to velocity. That's going to make a difference when you actually do the calculations, because something that is moving just a little bit faster will have just a little bit bigger momentum, but the kinetic energy is going to increase more because of that square. Okay, now let's think about, what if I have multiple objects moving? So my momentum for multiple objects would look like mass of A, VA, plus mass of B, VB. And notice, you can see all the little arrows indicating they're a vector. My kinetic energy is going to be 1/2 mass of A, VA squared, plus 1/2 mass of B, VB squared. So now let's think about the play, the interplay between these two, and ask a couple of questions. Okay, can a system have zero kinetic energy and non-zero momentum? Okay, well, let's go back. How can I get this to add up to 0? One of two things has to happen. Either my masses are 0, but if my masses are 0, my momentum's 0. Or my velocities are 0, in which case my momentum is 0. So the answer here is no. I cannot have 0 kinetic energy for my system and a non-zero momentum. Now let's look at the reverse of this. Can we have a non-zero kinetic energy and 0 momentum? Okay, so going back again. Under what circumstances could this equal 0? Okay, well, if MAVA equals negative MBVB, then this is going to add to 0. And this is completely doable because momentum is a vector and I can think about directions. All I'm saying here is the magnitude of the momentums of my two objects have to be equal, but in opposite directions. If this is the case, will my kinetic energy be 0 as well? No. Why not? Because that negative sign doesn't matter when it comes to energy. Right? If you want to think about it as the fact that the velocities are squared and a negative times a negative is a positive and it goes away, that's fine. Kinetic energy doesn't care about direction because it's a scalar, therefore it always just adds, so it doesn't matter. So when I come back here, yes, I can have a 0 momentum and a non-zero kinetic energy. And the way I have that is the momentum or momenta, I guess. I need to get my grammar correct. Momenta are equal and opposite. And again, this works because momentum is a vector. Okay. This one up here did not work because energy is a scalar and the direction cannot help me get the cancellation that I need.